a warm welcome to everybody here from the Institut de Recherche en Informatique Fondamentale in Paris. Welcome to the GReTA Graph Transformation Theory and Applications International Seminar Series, which is a new online series that will start today with a talk by Barbara König. So let me briefly introduce you to our team. I'm one of the organizers, together with Jean Crevin, also here at IRIF, and with Reiko Heckel at University of Leicester. And Reiko will be your host later today for the talk. And we are very, very lucky to also have a large scientific committee, currently consisting of 25 members. And the idea for this was that we would like to be a forum for this research field, and for this reason also reflect as many different topics, of course, as we possibly can from the field, and have a good representation. And as you can see from this list of upcoming talks, indeed we were already lucky to win some speakers for very diverse topics. So starting today with talk on graph transformation and model logic by Barbara König, and also we will have some applied graph rewriting talks, like for example about chemical graph transformations, and some talks about graph programming and about port graph rewriting and so forth. And as you can see, we still have a slot in January. This would be roughly bi-weekly. So if you are interested to give a talk, please do contact one of the organizers. And of course, again, starting from March. In general, we are aiming for a bi-weekly, so for a talk every 2 weeks. Okay, and information on the series, I guess you will already have seen the webpage, because this was a way to find information how to register for the Zoom meeting. Let me once again mention that to join a Zoom meeting of a particular seminar, you will have to register for it. And you can also only use the Zoom client, so you cannot use a web app. This is for security reasons. Alternatively, some of these meetings will be transmitted to YouTube, like more or less live. And also there's a mailing list and a Google Calendar if you wish to stay updated. So in general, please do get in contact with us if you have any suggestions. And once again, warm welcome. And I would like to pass now to Reiko to introduce the speaker of today. Thank you very much.
Thank you very much, Nick, also for setting this all up. Let's hope everything works as we hope it should. Okay, so yeah, it's my pleasure to introduce Barbara König. I just tried to find out how long we actually know each other. I think when we met for the first time, she was doing her PhD in Munich and I was doing mine in Berlin. So that was a good 20 years ago now. And I think at the time we discussed things like reduction semantics and type systems or something like that, if memory serves. And in the meantime, she's been busy working on unfoldings for graph transformation systems, which is a new sort of concept she came up based on the theory of Petri nets, and generally always looking at concurrency theory and concepts from that area and how they could be sort of applied and imported, if you like, into graph transformation. So that was a sort of ongoing theme throughout a lot of her work. And that includes obviously relation between rewriting and logic, which is what she's going to talk about now. So I'm not going to give you a full CV. You can read that in the web page, but I hand over to Barbara now for her presentation. Please, Barbara.
Okay, Reiko, thanks a lot for the introduction. So I will now share my screen. I hope that everything goes well. So now you should see my slides, right? If not, please complain. Okay, so thanks a lot for giving me the opportunity to give this talk. I think this is a very nice idea to start with this seminar series, and I'm happy to be able to give the first talk. I had a few Zoom hiccups problems this week. I got frozen in some Zoom conferences. I hope that this will not happen again, but so far things look good. So now about the talk. The title is Graph Transformation Meets Logic. And I decided that it might make sense to give a bit of an overview talk. So you already see the references that are here below, some of them are a bit older. So this is an overview over things that are part of them already well known. Although I also give a bit of my personal view on the topic, and that is maybe a bit non-standard and not really known to everybody. So this is joint work with many people, with Sandra Brüching, Raphael Coderlier, currently with Andrea Corradini, also with Matthias Hülsbusch, Sebastian Küpper, and with Lars Stoltenau. Okay, then when I prepared this talk, I thought, okay, with all these online seminars and so on, I should do a quiz, but then I couldn't really think of any good quiz questions. So what you have to do now is to make sure that this is going to be interactive and ask questions in the chat. I kind of see the chat, but I think that Reiko will also monitor it and pass all relevant questions on to me. So feel free to interrupt me during the talk, and I'm happy to answer your questions. Okay, so I'll start fairly generally, so I can try to make this as accessible as possible, and I'll talk about just first what are graph transformation systems. And for me and for many other people, graph transformation systems are a computational model for dynamic systems. And you have to view it in this way, that the graph represents a state. So the graph is a state, and the production applications are the state changes. So there are rules, and the rules consist of a left-hand side. I hope you see my mouse, do you? Yes, okay, you see the mouse, very good. And the left-hand side is always replaced by a right-hand side. And these blobs that I have here, the red blob and the blue blob, they're supposed to be graphs. There are some specific fixed nodes, which are the interface nodes. And then you look for the occurrence of a left-hand side in a larger host graph. You remove the left-hand side, but keep the interface, the white nodes in this case, and you replace it by a right-hand side. So that's graph transformation on a very superficial level. And so why is graph transformation nice? Well, you can model systems with infinite state spaces. You can easily model dynamic creation and deletion of objects. You have a straightforward modeling of mobility features. You can model variable topologies. So you have a very, very rich modeling language, but of course, rich modeling language all sometimes get complicated. And then there are some problems with verification, some challenges there. Okay, so there were two keywords in the title, graph transformation and logic. And so now we are talking about why do we want to enrich graph transformation with a logic? I mean, graph transformation is already a powerful modeling specification language. Why do we need logic? And well, there are several answers to this question. And the first is you want to control rule applications. Maybe you want to be able to replace the left-hand side by a right-hand side, but maybe not in every context, but only if some additional conditions are met. And this is, I think, also the way how conditions were originally introduced into graph transformation. What do you also want to do, especially if you come from verification? You want to symbolically represent and manipulate sets of graphs. And these sets of graphs are very often infinite. And you want to have a finite means by a formula, by a condition, to describe this set of graphs and then somehow manipulate it. And then this is connected to this. You want to verify graph transformation. So you want to compute preconditions, postconditions, Hoare logic, and then of course you also need a logic that is integrated with your approach. You maybe want to write queries for graph databases, also very interesting topic nowadays. And you just want to obtain a richer modeling language. I mean, same as object constraints logic was added to UML. You want an additional logic that gives you additional specification mechanisms. And so here, actually, I only want to talk about first order logic. Monadic second order logic would also be of great interest. So especially if you look into the work of Courcelle, for instance, Courcelle worked a lot on monadic second order logic in connection with graphs and the connection to recognizable graph languages and so on. And all of this would also be of course, very interesting. But this talk is only about first order logic and not about second order logic. Okay, so let's start a bit with first order logic. So let's maybe try to formulate a condition on graphs using first order logic. And I want to say that the source node of each A-labeled edge has a B-labeled loop. So let's just say this in first order logic. So the syntax is not so important, but we could say that for all edges E1, if the label of E1 is A, this implies that there is another edge E2, such that the label of E2 is B, and the source of E1 is the same as the source of E2, and it's the same as the target of E2, so that you know that B is a loop. This is something you can say in first order logic. Instead, what people in graph transformation are usually doing, they're using graph conditions. And graph conditions means you have something like this. I mean, you have actually a condition that contains graphs themselves. And so maybe forget about this empty graph here at the beginning right now, but there's a universal quantifier that says for all occurrence of this graph here, which is two nodes connected by an A, there exists that you can extend this graph to another graph that contains also this A edge plus this B loop on the first node. And you basically start with the empty graph. You have there are morphisms also in there, graph morphisms, structure preserving mappings between graphs, and you map this empty graph here to this graph and this graph into this larger graph. So it says basically whenever you can extend the empty graph by a graph that contains an A edge, there also has to be a B loop. So this is more or less the way that people in graph transformation systems work with conditions. They're using this type of thing. But why do they do that? So why are these graph conditions interesting, and why don't we just say, okay, there's first order logic and we use that? Well, first, conditions are able to express properties more succinctly. So you can somehow more directly express things about your graphs. That maybe you also already saw this in the example. You directly see the graph in the formula. Then also there's a question of uniformity. So since both the graphs that you rewrite and the conditions are somehow from the same universe, both consist of graphs and graph morphisms, you can use similar constructions in both worlds. Then there's also one very nice thing you can do with the graph condition that I just showed you, that is not, or I have no way of doing this directly in first order logic, is you can do some kind of partial evaluation or shift. I'll say later more about what this means and why it is interesting. And actually it's a very important operator that you need a lot when you work with these conditions. And also, so if we have another view, it gives us a possibility to generalize with respect to the underlying category. So you could use, instead of directed graph, hypergraphs or undirected graphs, or this is something that I will later do Cospans instead of graph morphisms. And I'll tell you why this is useful. Okay, so this is again a slightly different view, but of equal expressivity than the more classical first order logic. Okay, so this is a bit the general introduction. What are we studying? Why is this interesting? And now the overview of this talk is as follows. I'll first introduce double-pushout graph transformation, which most of you already know, but just, I mean, maybe not everybody knows. And also it will be important for what is happening later. Then I'll talk about conditional reactive systems. This is kind of the new or not quite so standard contribution, which is a very general framework for rewriting, but also very general framework in which to incorporate these forms of conditions. And then I'll keep working in this general framework and also say you something about operations on conditions such as shift, axioms, And then I'll say a bit about applications, how to compute pre and post conditions, critical pair analysis. Let's see how much time I have. So maybe I'll cut the critical pair analysis a bit short, and I'll say a few words about bisimilarity. And then I'll say something about satisfiability, how to check whether a condition is satisfiable, so has a model. And then I'll conclude. Okay, and I saw that Detlef had a question, which I'll now read. The pros for graph conditions are insider arguments. What about the readability of for users of graph transformation who may be familiar with first order logic, but not morphisms? Yes, okay. This is of course a point, readability. But on the other hand, of course, you can switch between both formalisms. You can, if you want, from one to the other. I mean, there are encodings from one to the other. So maybe you could let users specify things in first order logic if they prefer, and then shift to the other world. Especially some of the constructions, such as shift, I think are really, I have no idea how to do directly on first order logic. Okay, I hope this helps. And then let's just quickly talk about double push-out approach. And so assume we have a rule. And the rule consists of a left-hand side L here. So I hope you see my mouse. If you're not, please complain. Then there is a right-hand side. And then there's an interface that occurs both in the left and the right-hand side. So there is a morphism here and there. And these upper morphisms are nonsense because they should only go from left to right. Sorry. So these ones should only go from left to right. Okay, and these are all graphs. So L, I, R, G, C, H are all graphs. And the arrows are all graphs morphisms. And the squares are push out. So what does it mean to have a push out? I mean, especially look at this left-hand square. It means that if I glue the left-hand side L and some context over their joint interface, then I get G. So if I can construct G from the left-hand side and the context by gluing them together via push-out, I can also take this context, glue it to the right-hand side and get H, which means that I rewrite G to H using that rule. This is an example now with the arrows all going in the right direction. So I have a rule, and the rule says, if I have a connection between two nodes, this is this C here, and there is an M loop, M is supposed to be a message, then I can move this message from one node to the other, so the message kind of goes or is sent through the network, and it moves from here to here. And now this left-hand side occurs as a match in this graph. And there's another edge, this is this N edge. I'll talk about this N edge later, what that actually means. And then in this setting, you can remove everything that is in the left-hand side, but not in the interface. You get this context graph, which glued together with the left-hand side would get you G again. And then I'll put this together with the right-hand side, do the push out, and I'll get this. Okay, good. Just very, very basic, very standard. Now let's go to the next step. So we want to talk about conditions. So next step is to talk about negative application conditions, just negative. So we want to say we can apply the rule, but only if in the vicinity of the left-hand side says some structures are not present. For this, you take the left-hand side and you take a morphism into N, so some other graph. N is also some graph. And you say, I can apply this rule, but only if there's no morphism from N to G that makes this triangle commute, which means that this negative structure into which you embed the left-hand side cannot be found in the graph itself when you consider the position of the left-hand side. So you should not have any morphism that makes this commute. Often you require that this morphism is injective, but okay, this I'll skip a bit about this detail. So now let's come back to the example. So we have this graph, and this edge N is now interpreted as noise. So if I have a connection with an N edge in parallel, there's some noise on the connection. So the connection is unstable, let's say. And so the left-hand side here that I have, the negative application condition that I have here says it's the same as the graph. Says I can only apply this rule if this noise is not present. So if the condition or the connection is without noise. But of course, here there is a morphism that makes this commute, and this triangle would commute. And so there is noise, and this keeps you from applying the rule. And okay, we cannot apply the rule in this setting with these negative application conditions because this is forbidden. Okay, these are the very basics of negative application conditions. And of course, now we'll extend these conditions and come to a more general setup. So I tried to assemble a history of graph conditions. This is a bit of a slippery slope because I know I might have overlooked something. I tried to do some research and try to follow the references. But okay, if I overlooked your paper, please bear with me and tell me later or during the talk. So I tried to track the origin of negative application conditions, and the first paper that I found was one by Hartmut Ehrig and Annegret Habel from 1986. So it's the first one that I found. And there's another paper 10 years later by Annegret and Reiko and Gabi, which picked up this idea and then developed it further. Then, who was the first person to consider nested conditions? So not just negative conditions, but let's say nesting of quantifiers. We'll come to this later. Actually, the first paper that I found was the one by Arend Rensing in 2004. Very nice paper, where he also shows the equivalence to first order logic. And then there was a generalization of all these two adhesive categories, various expressivity results, proof rules, tools for nested application conditions, and so on. There's a lot of work by Hartmut and others, and also in particular by Annegret and together with Karl-Heinz Pennemann, who wrote his PhD thesis on the topic and got very nice results there. Then, well, we did something in 2011. We generalized to reactive systems. This is also something I want to talk about in this talk. Then there was a very nice result by Lynn Lambas and Fernando Rejas, and then also together with Sven Schneider, who did tableau proofs and model generation for satisfiability. I think this is quite impressive. And then, of course, in Holger Giese and Lynn and all other people in the group in Potsdam, they're working on tools using verification, graph queries. And then now, of course, I forgot quite a few papers, I guess. So I'm sorry if I forgot your paper, but please send me a link. And I'm aware that, of course, that there are many more publications. Okay, so now let's come to this, the part on reactive systems. So because I wanted to give you somehow maybe more abstract view on graph conditions that is not so common, but I think that is very useful because in this abstract layer, actually, you can hide a lot of complexity. The constructions are as complicated as they were before, but still many things can be expressed quite clearly and elegantly in this setting. And for this, I'm using the framework of reactive systems introduced by Leifer and Milner in 2000. Concur paper 2000, and it's an abstract theory of rewriting. It's even more abstract than double-pushout rewriting and subsumes double-pushout rewriting. So this is a very general framework. It encompasses term rewriting, process calculi, graph transformation, bigraphs, Petri nets, whatever. Everything you want to rewrite, you can probably rewrite in reactive systems. And the original motivation of Leifer and Milner was that they wanted to consider a rewriting framework that produces unlabeled transitions, and from this to derive labeled transitions. On top of that, do bisimulations, define bisimulations, behavioral equivalences, and in such a way that the equivalences that you get are congruences, are preserved by contextualization. I will talk only very shortly about bisimulation at the very end, because my main motivation now is I want to use reactive system and now enrich them with conditions, because actually most of the things that have been done with conditions already work in this general setting. And of course, you use conditions similar to graph rewriting. You check whether a rewriting rule can be applied. And this gives you conditional reactive systems. But let's first say, what is a reactive system? Just going back to Milner's and Leifer's original theory. So a reactive system is always over some category C. I'll say what the example, I talk about example categories shortly. What you do is you rewrite arrows. You do not rewrite the objects of the categories, but the arrows of the category. And you say you have an arrow A and you factor it into a left-hand side and a context. And then you replace the left-hand side by a right-hand side, which is also an arrow. And then you compose this with the context, and that's it. This is the definition. It's very short. So you start with some distinguished object 0, which think of it as the empty graph or something, some empty thing. And a rule consists of 2 arrows, L and R, going from this distinguished initial object to some object I, some other object. And then the reduction relation is just, let's pick context, which is just some arrow from I to J. Then composing L with C and R with C, you get a rewriting step that transforms LC into RC. Or in different words, you can rewrite an arrow if it decomposes into L and C. And then by rewriting, you get R and C. That's all. Now, of course, we have to see what this means and how it matches our intuition about rewriting. Also, in what sense does it encompass double-pushout rewriting? So, but before that, I wanted to give you an example. And the example is the following. We consider Petri nets. This is inspired by a paper by Vladimiro Sassone and Pavel Sobocinski. And you take a Petri net and you view it as somehow an arrow. So you have input places, but okay, there are no input places. So this is kind of empty, and output places. And then you want to fire the transition. So for this, you decompose the Petri net into 2 parts. So the left-hand side is the transition that is really interesting and you want to fire. And the right-hand side is the context. So that what is not involved in the transition, in the firing. Then this is the split into left-hand side and context. Then you replace the left-hand side by the right-hand side because you fired the transition, this changes. You compose things again, and this simulates the firing of the transition. That's it. Okay, so this is kind of the intuition. And now let's talk about how to instantiate this. I mean, which categories do we actually want to use? So there are 2 interesting categories that one could use. So the first is just the standard well-known category. We use graphs as objects and graph morphism as arrows. And if you want, you can restrict to injective graph morphisms if you have some injectivity requirements. Or the other, maybe more interesting category is the one where objects are again graphs, but the arrows are now cospans of graph morphism. So what is a cospan? A cospan consists of 2 morphisms of this type, one going from J to G and the other from K to G. So you can also think of it, if G is a graph, let's say, or these are graphs, then G is a graph in the middle, and the graph has 2 interfaces, an inner interface J and an outer interface K. So think of it as a graph in the middle with 2 interfaces on both sides. Actually, to be a bit more precise, if you want to really work this out, you want input linear cospans where the first leg is injective, but I'll skip that detail. So what is the intuition for these Cospans? I already said you think of them as graphs, or maybe not just graphs, could also be other things, with an inner and an outer interface, and composition is performed by gluing over this joint interface. So you have two Cospans. So the first one goes from this green interface into the blue interface, and the other one goes from the blue interface into the red interface. And now, if you want to compose these two Cospans, what do? You take the inner interfaces, or let's say the outer interface of the first and the inner of the second. You just, they're equal, so you just identify them, and you take a push out, and this gives you this graph, and you forget about the middle interface, and then you've done the composition of the Cospans. So you just glue over the common interface. Completely straightforward. Okay, then let's now take reactive systems and instantiate them with the Cospan category. So the arrows are now Cospans. And we think about what this has to do with DPO rewriting. So this is the standard DPO diagram, this times with the arrows in the right direction, fortunately. And there are 6 graphs and 7 morphisms. And but where are the Cospans? There are no, but you cannot really see them yet. So what you do, you add 3 more things. And you add 2 empty graphs at here and here, at the right, at the left and at the right. And 2 morphisms, and this makes the diagram commute automatically. And below here, you add another graph, which is the interface of both G and H, the joint interface of these 2. And you can also take the empty graph if you like. That's also fine, but okay, let's take just some interface. And then where are now the Cospans? Well, there's here the left-hand side. This is a Cospan going from the empty graph to I. The right-hand side going from the empty graph to I. The context, which is an arrow going from I to J. And if you compose the left-hand side and the context, you get the graph G to be rewritten. And if you compose the right-hand side and the context, you get the graph H, which you get as a result. So let's abstract from that, forget about graphs and graph morphisms, but look at the Cospans and the Cospan composition instead. And here are the Cospans. You have L composed with C, which is G, is rewritten to R composed with C, which is H. Okay, so if you want reactive systems, generalize yes, DPO rewriting if you take as a category the Cospan category. Okay, so next step, now I want to integrate conditions into reactive systems. Let's start with negative conditions. Okay, this is a negative condition. I just drew this diagram slightly differently. We're here with a negative condition on top. So now we have one problem because the L is actually inside a Cospan. You cannot access it in reactive systems. There's no way to talk about this L. It's hidden inside the Cospan. So you cannot really do this. But actually there's an alternative equivalent. Instead of interpreting the negative condition over the left-hand side, you can move it to the interface. How can you move it there? You take a push-out complement. So make sure that this upper square is a push-out. And then actually checking whether this morphism doesn't exist, the one from M to N to G, such as it commutes, is equivalent to showing that the morphism from N prime to C does not exist, so that this triangle here commutes. So this is equivalent. So you can say, okay, but then push-out complement need not exist. Yes, might be the case, but then this actually, the NUX already is subsumed by the dangling condition and you don't actually need it. So you can also, the first lesson learned is you can also put the negative condition on the interface, which is better for reactive systems because the interface you can access somehow. Then, since we're already on the interface, we can also transform this into a Cospan. I mean, here I just put the identity here up here, but you can do a general Cospan if you like, and then interpret the condition such that you say there's no Cospan from here to there, such that this composed with this gives you this. This is the same way of interpreting the condition, but now on Cospans. Okay, and more or less that's what it takes. And then we've already integrated negative conditions into the reactive system framework. Okay, so next, I now want to move away from these negative conditions and go to general nested conditions but now over arbitrary categories in an arbitrary reactive system setting. So what is a condition now? So I said I want to nest things now. And a condition is a finite tree where nodes are labeled with objects. So these here are nodes, and they're labeled with objects of my category, graphs. Think of them as graphs. And then at each node, there's also a quantifier, universal quantifier, existential quantifier. And then between two objects, if there's a graph edge, there's an arrow of the category here, an arrow from A to B. Think of them as Cospans, or also in a simpler setting, just graph morphisms. This is more or less similar to the conditions that Arend Rensing considered, and also very similar to the ones that are considered nowadays in graph rewriting. And this object A here is also called the root object of the condition. And negative application conditions are a special case where you only have one universal condition and then an empty existential condition, which means that for all ways to find the negative condition, there exists nothing which empty existential quantifier is just false. So then you get a falsity. Okay, let's look at this. At this example, I see there was also a question in the chat, which says, if you put the negative condition on the interface, are you losing some expressivity? You mean instead of putting them on the left-hand side? No, I mean, of course, I have to show, this has to be proven, but prove this. No, you don't, because actually, if you cannot move it to the interface, then actually there's something wrong with the dangling condition, and you cannot apply the rule anyway in this setting. So of course this has to be spelled out, but it's equivalent. Okay, so let's do an example. So maybe it's now really do a Cospan condition as opposed to a condition just on with morphisms, and we want to interpret this for a graph. And so, okay, everything is a Cospan, so you have to equip it with two interfaces, empty inner, empty outer interface. And we want to say that a Cospan, this graph contains an contains an isolated node labeled A. So you just say something like this. There exists a Cospan to the empty graph such that for all empty universal quantification is true. And the Cospan is just you have an isolated node in the middle. This is a graph consisting of a single isolated node. And what you say is basically G must satisfy the property that it can be decomposed into this Cospan and something else. And in this setting, if it can be decomposed into this Cospan and something else, it means it contains this node as an isolated node because there's nothing in the interface to connect it to anything else. This is not so easy to express with classical conditions where you don't have Cospans, but just morphisms. But okay, you could, if you have finitely many labels, you can do it by saying there is a node that is not connected to any of your edges. But if you have infinitely many labels, this will be difficult. But is there any advantage of the Cospan conditions? Well, you're a bit more expressive. It's easier to integrate them into the reactive systems. It's easier to express that nodes are isolated, so these kind of dangling conditions. And you also have the possibility, this is for convenience, to forget graph elements in the condition. I mean, you do not have to, otherwise you always have to keep the left-hand side and extend it with more and more and more stuff. But in this case, you can forget. Actually, other logics also handle this. They have some syntactic sugar for doing this. Now, the question is, now we have a condition, which is this, remember, this is condition is this tree here equipped with quantifiers, tree with objects and arrows. And now we have an arrow from A to B, and we want to know whether this is satisfied by the condition. Or whether the condition, whether this is satisfied with the condition. So, and so on, what do we want to check? So we have to distinguish two cases. First, whether the root node is universally quantified, and the other is whether the root node is existentially quantified. And if the root node is existentially quantified, is universally quantified, what do we do? So we have this C, which is an arrow from A to B, and we require that whenever this arrow C decomposes into Fi, so one of these outgoing arrows here, and some other alpha, then this alpha must satisfy the condition which comes afterwards. Okay. So, and now we want to check whether C is a model for the condition if the root node is existentially quantified. And in this case, so again, we have this C, and we require that this C decomposes into some arrow Fi plus some alpha. And then also we require that this alpha satisfies the condition that comes afterwards, after the Fi. So it's sufficient to have one Fi, so that C decomposes into Fi and something else, and then this something else must satisfy AI. So actually, it's more or less, it's the natural thing, what you would expect, but of course it has to be specified. So what we also did, but this is kind of more or less generalizes Arendt's result, we said that if we instantiate now these conditions or this reactive system setting with adhesive categories consisting only of monos, we get some logic of on sub-object, first order logic on sub-objects, which is a slight generalization of the result that it was already there for the graph case. And so if you really go to graphs and graph morphisms, you get first order logic. But if you have Cospans, you're actually more expressive because you can express these dangling conditions that you cannot express that straightforwardly directly in the graph morphism setting. Okay, so then I want to start talking a bit about the operators that we have. And one of the really fundamental operators that you have is the so-called shift, which is really very nice. And I think it's really one of the reasons why you want to work with this form of graph conditions. Think of it as some form of partial evaluation. So, and okay, so the setup is the following. We have an arrow from A to B and a graph condition with root object A. So it sits here on top of that A. And now you want to move this condition to a condition with root object B, which is called A shifted over phi. So A down arrow phi. And how do you characterize this condition? So it's a condition with root object B. And it should satisfy the following. If phi composed with some C, so this semicolon is just composition. We had this before. If phi composed with some C satisfies A, this is equivalent to C satisfying A shifted over phi. What does this mean? It means that we have this condition A, and now we want to view it in a context where we already know that every of my arrows on which I want to interpret this condition, which I want to look at, starts already with phi. So we can kind of change this condition, change it in such a way that we only check it on C, and it holds on C if and only if it would hold if we prefix C with the phi. So we are in a setting where we already know that my arrow starts with phi. So this is just a definition. It doesn't say anything whether this can actually be constructed, whether we can get such a tree, but it can. So, I mean, okay, you need some requirements on the category, because what you have to do is you have to take A and phi and do a lot of overlapping of the two. And so for this, you need some constructions. So in the standard graph setting, it means taking a lot of jointly epi morphisms. You can also use so-called borrowed context diagrams in the Cospan setting, or Leifer and Milner would call this item pushouts. You need a certain construction of doing so-called representative squares. And I won't go into the details. It's interesting, but I don't think we really have the time to delve into this too deeply. And let me warn you that this is expensive. It's very nice to do this, and it's very useful, but it costs you a bit, just because you have to look for all possible overlaps of things. Okay, then you can also, there are some laws that make sure that this is all nice. So consider now the set of all conditions with root object A. You can view this as a category with implication as arrows, or as a lattice with disjunction and conjunction. I didn't really talk about disjunction and conjunction and negation. They're derived operators. So you can get disjunction by existential quantification and conjunction with universal quantification. And negation you get by exchanging the two types of quantifiers. So if you view this now as lattices, then actually we get two adjunctions. And the one is that existential quantification and shift form a Galois connection. So existential quantification is the left adjoint, shift the right adjoint. The same for shift and universal quantification. So I'm drawing this here. And so the existential quantification takes a condition over A and takes an arrow xi, and just prefixes this with an existential quantification over xi. I mean, you could just prefix the tree with another edge to the root. And you can go, this gives you a condition over B, because xi goes from B to A. You can go back by doing the shift over xi. And this is it's an adjunction. So more concretely, it satisfies these adjunction laws. So A implies if you first existentially quantify and then shift, and if you first shift and then existentially quantify, this implies B. This is just the property of an adjunction. And same for shift and universal quantification. I think this is quite nice. Shows that this is kind of natural, the good operator. There are lots of other operators that kind of are natural. I mean, since shift is both a left and a right adjoint, it preserves both infima and suprema, so conjunction and disjunction, and universal quantification only satisfies conjunction, and existential quantification disjunction. That's kind of the normal thing. Okay, then what I haven't really said is now what is a reactive system enriched with conditions. So again, as before, we have rules. Okay, Detlef was just asking whether there's a logical characterization of the expressiveness of conditions based on Cospans. Good point. Yes, we have shown actually that there are more expressive than first order logic. I mean, basically based on the example. But an exact characterization we don't have. So in some papers we wrote they are slightly more expressive, which the reviewers didn't quite like, and they're kind of right. So no, I do not have a very good answer. It would be interesting to explore this further. Okay, sorry, I was talking about this conditional reactive system. So you have rules as before, and now every rule is equipped with an application condition with root object I that sits on the interface. And then a rule is applicable to an arrow if you can compose this arrow left-hand side context. The context must satisfy the condition. And then the left-hand side composed with the context rewrites to the right-hand side composed with the context. Okay, just a small example, but this doesn't really say so much more. So we have here a rule that in a system that shows that where you have a user who owns a file, U owns F, and we want to dereference it, so this own link should disappear. And you say this can only be applied if the file is not protected. So whenever the file is protected, you can only apply the rule if the user is an admin. So whenever the file is protected, there exists this admin loop. And then the empty universal quantification, which is just true. So the conditions restrict the context in which a rule can be applied. That's basically the story. Okay, then this is more or less the theory. Now I want to talk a bit about applications. The applications are not just applications for conditional reactive systems. Of course, they have also been worked out in the graph transformation setting, but here I can state them in this more general setting. Okay, so assume you have a rule, left-hand side, right-hand side, and a condition. So the rule can only be applied under some condition. And A and B are also conditions on the source of a root object 0. And now you will want to compute weakest precondition and strongest postcondition. Let's start with weakest precondition. So weakest precondition means I've characterized a set of arrows, object, graphs. Think of them as graphs. I have a set of graphs, and I want to know, and I've characterized them with a condition. And now I want to characterize those graphs that if I could apply the rule, I would end up in a graph that satisfies this condition B. This is the weakest precondition, so the predecessors basically. And so you want the weakest precondition given a rule R and a rule B. So which graphs have the property that if I can apply R, I for sure end up in something satisfying B. So what you do is you say, okay, I need this here characterizes these arrows. It says, okay, whenever my arrow contains a left-hand side. If it doesn't contain a left-hand side, I don't have to do anything anyway. If it contains a left-hand side, so for all cases where I start with the left-hand side, and I satisfy the condition, so I can apply the rule, then what I get satisfies B if I would prefix it with R with the right-hand side. This is what this says. So I characterize the set of arrows or graphs such we can guarantee B after applying this rule with condition C. Or I can also do a strongest postcondition, which is, so I have a set of graphs A, and I want to characterize those successes that I get by applying R. So I say something like, okay, since I just applied R, there must exist a right-hand side, there exists a right-hand side, such that the remaining context satisfies the condition. And if I would prefix this thing again with L, this must satisfy A, because A is where I started from. Okay, so I see Fernando's question. Let me just finish and then I'll try to answer it. And I think this is fairly straightforward. I mean, of course, there's a lot of complexity hidden in these fairly simple looking formulas, because shift over Cospan is nothing to be trifled with. It's a fairly difficult operations, but on this abstract setting, you can state it in a fairly elegant way. Of course, if you want to do the construction, you will run into trouble. I mean, not trouble, but this will be costly, but this is interesting. So I'll just try to see what Fernando wrote. In most approaches using graph conditions, it is assumed that morphisms used in conditions and morphisms used in satisfaction are monos. However, if you lift these constraints so that in both cases you can use arbitrary morphisms, then shift is not expensive anymore. Actually, in this case, shift is just a push out. Yes, yes, this is true. This is something I slightly glanced over. So I said it was a bit hidden in this notion of representative squares. If you don't use injection, then the shift is just and you just use a standard morphism, then the shift is done by pushouts, and it is not expensive at all. That's true. But of course, people do use injective morphisms because it's more expressive, and with other morphisms, it's often very difficult and very cumbersome to express the things that you want to express. So I think there's a trade-off, more efficient shift, but more problems modeling things or expressing things. And maybe it would be interesting to investigate this trade-off more, and maybe it's useful to use also allow non-injective morphisms, because then the shift becomes less expensive. Actually, here I'm thinking of Cospans, and then of course it's not so easy because there are no pushouts in the Cospan category, and we did input linear Cospans mostly, and the shift is expensive then. Yes, yeah. So Fernando is saying, yes, there's a paper by Annegret and Karl-Heinz, which we looked into also recently, where show that they have the same expressive power. But I think still the encoding is such that if you start from condition using only monos and go to other conditions, then it's a bit cumbersome to encode this condition. So you need larger conditions to express the same thing. But still, yes, I'm not sure this trade-off has been fully explored yet. I think, okay, good. Maybe let's not go into, maybe we can talk about this later and discuss the various expressivity results later in the discussion. Okay, so then there is actually one thing that I already expected that I might have to glance over it, which is Confluence without and with conditions. Let me just say very quickly that if you want to analyze local confluence, you can do it by critical pair analysis. So you take two left-hand sides, consider all overlaps, do a step from this overlap, do a step by applying rule 1 and rule 2, you get this kind of V-shaped diagram. And if you're always able to close it by rewriting it to the same joint target, then you can show local confluence by analyzing all critical pairs. And just to say that this also works with conditions, but then you have to say something about an implication on some conditions and so on. It's a bit more tricky, but it works as well, although it's not an if and only if condition anymore, but just in one dimension. Okay, then another application that I also want to just mention fairly briefly is behavioral equivalence. This is something that we now recently worked on. There's a 2020 paper in FSCD. And so the question is, there are two arrows, and we want to say whether two arrows are behaviorally equivalent or bisimilar in all contexts that satisfy C. So they might behave differently in other contexts, but we want to say that when the context satisfies C, they behave the same. And so this can be done by generalizing this borrowed context approach, both to conditions on the rules and conditions that constrain the environment. And the application, for instance, model transformation, that you want to say, I transform this graph in such a way, I want to show that it still has the same behavior, but maybe I do not have to consider all possible contexts because not in all cases, because not all possible contexts are feasible. I mean, not everything is a valid model. Okay, then I'm close to finishing, but I wanted to first say something about satisfiability. I mean, all this looks very nice, but keep in mind that this is first order logic. So satisfiability and implication are both undecidable. This is bad. Although it's semi-decidable, so there are semi-decision procedures, resolution, tableau proofs, model construction, if a finite model exists. And there's very nice work by Lene and Fernando, who introduced a tableau proof for nested conditions based on previous work by Pennemann. And Karl-Heinz Pennemann also showed that actually for graph transformation case studies, there is a gain in efficiency. So it is useful to do special purpose theorem provers as opposed to using generic first order theorem provers. And our idea is also to generalize this to the reactive system case, which we haven't done yet. So this almost concludes the talk. But I have one finishing slide. So future work, I have one idea. So something that is not really fully worked out in my mind, and maybe this could be interesting for discussion. Whether maybe one could study in more detail the relation between graph conditions and separation logic. I mean, separation logic is a very successful framework for verifying pointer programs, heap structures. There's a lot of publications on it. And there's one operator that is called the magic wand that kind of in some way looks a bit related to a shift. So I wonder whether this has been studied in more detail. But there are, of course, papers explaining the relation between separation logic and hyperedge replacement grammars. So, so in that sense, this has been studied, but maybe there's more to be said about this story. And then I want to conclude with one application that we also have in mind, and that is doing counterexample guided abstraction refinement, so-called ZGAR approach, which is important approach for program analysis. And so basically what you could do is you represent sets of graphs by conditions, and then you apply rules and you compute the strongest postcondition, and then you have a representation for the successor graphs. And in this way, you construct an abstract transition system on conditions, but conditions representing sets of graphs. And you can do verification, and then you could use all these ZGAR ideas for verifying your graph transformation system. I mean, you certainly have to, there are some hurdles to this. I mean, because it requires deciding the implication problem from time to time, and this is undecidable. So you need approximative methods, or you structure a simpler logic. Or maybe do graphs of bounded tree width only, because then the problem becomes decidable. So you have to do some workarounds. But okay, in general, first order logic is also undecidable, and people have worked with this in the ZGAR approach. So maybe this is feasible. Sorry. Okay. So I'm now at the end of my talk. So this was the last slide. And thanks for listening. Thanks for coming. And I'm looking forward to your questions.
Okay, thank you very much. Yeah, so for questions, I suggest that we try to do this a little bit more interactively. So it's an experiment. We haven't tried that before with that large number of people, but could we just do the traditional Zoom thing? So you raise your hand in Zoom if you want to ask a question, and then we will basically allow you to ask the question directly rather than having to type it into the box here. Yeah, could we do that? So I think I have to show the participant list in order to see what you're actually saying. So let me maybe make a start, and then we can see who else has a question afterwards. So I was interested in this last point, in particular, the question about separation logic, and I looked at that some time ago, just to try and understand how that would relate to our concepts. And my impression was that they work with a composition operation that is not so much graph gluing, which is obviously what at least graph transformation in the double push-out approach is based on, but much more like disjoint union and connecting, because it's essentially taking the disjoint union of two sort of areas of memory and then establishing pointers between them. So therefore, it's more like disjoint union and connecting. So I wonder whether we have the right, whether the gluing approach, if you like, double push-out, is the right sort of semantic framework for that.
Yes, I don't know. So, I mean, I'm not such a big separation logic expert, but of course, I mean, I've looked into it and I talked to people. And certainly, I mean, their approach to combining graphs is, I mean, let's say from our point, I'm a bit more hands-on, ad hoc. You do some kind of disjoint union and no universal construction or gluing as maybe we have in mind. So, I mean, yes, maybe it's not so easy to compare, but I mean, people have compared via hyperedge replacement. So I think there should be some formal comparison. What I think is, okay, this is a bit imprecise, but the separation logic always says it is, they say it's so successful because of separation, because they do not, if they have a formula and they talk about some part of the heap, and then some other part of the formula talks about the part of the heap, you know that it's not the same part. So you have this separation of concerns, and you really know you talk about different parts. And this is exactly what also the conditions do, because they also separate. I mean, if you have seen something, you will not see it again, basically. And so, yeah, I mean, this is my feeling. It's not really fully thought out. It was more like an avenue for future work.
Yeah, no, I agree that it's essential to separation logic that the domains are disjoint essentially. So that makes sense. Okay. So yes, I mean, we had a discussion earlier with Detlef and Fernando. So I don't know whether I can. Have you unmuted yourself already? So maybe I can unmute both of you. You can unmute yourself, and then we can have a sort of three-way discussion in a way. But Detlef can probably start, and Fernando.
Okay, so I have just one quick comment and one question. The quick comment is on the decidability issue, which Barbara mentioned. I don't think it's, I probably agree with you. I think it's a non-issue. I mean, at least if we talk verification, theorem proving is undecidable, right? So it's even in first order logic. So it's nothing new. I wouldn't worry about that. So it just happens to be the case. And as you say, you have to look for sufficient conditions, special cases, and so on. But I don't think it's a principal problem. It's just my view on that. The question is on this. Expressiveness again. I mean, I agree. The graph conditions are an interesting alternative or view on first order logic, whatever you want to say. But then if we stay in classical logic, you know, it's very easy to extend. And you yourself mentioned monadic second order logic. But then can we still do something like that with graph conditions? So I haven't seen any version of, I mean, I know there was a bit of work or tries in Oldenburg to do something having something more powerful, but you know, do we have a graph condition formulation which equates, let's say, monadic second order logic or even more expressive ones? Because as we all know, yes, first order logic is really weak if you want to have basic properties like connectedness of a graph. There exists a path of an arbitrary, all these things which are extremely important in practice, especially in all contexts of graph programs. You know, if you want to say something about a graph algorithm, you need these things all the time, and you naturally come to an area which is beyond the reach of graph conditions and first order logic.
Yeah, it's of course true that you easily kind of hit a boundary, because then you need more expressiveness than you actually have in first order logic, like existence of a path that connects this and this. Yes, this is this is a bit problematic. And then of course you would like to do monadic second order logic, for instance. But then, of course, things get more complicated. I mean, of course, there have been some attempts to enrich conditions with this. And of course, then when you go to this, you have to look into the work of Courcelle, because whatever you want to do with monadic second order logic and graphs, Courcelle has done it before, more or less. And so what you can do is, of course, you can do an automaton model then for graphs, because monadic second order logic characterizes the recognizable graph languages, and there's an automaton model for graphs, which recognizes graph languages. And you can start working with this model. But the problem, I mean, we also did this, but the problem is these automata are really huge. They are very, very large. And this is mainly because there are so many ways to decompose a graph. There's no different than from words or trees. There is no canonical way to decompose a graph. I mean, people tried, but so the automata are huge. And then you have to represent the automata. And so you have to have a symbolic way to represent the automaton. And okay, I mean, you can all do all this. Maybe we still need some kind of breakthrough to make this really more manageable, because then things are starting to get really difficult and really tough.
Yeah. Okay, if I can just make one extra comment, just a little advert. So my PhD student, Gia Wulandari, she is just finishing her thesis on using MSOL for Hoare logic for graph programs. So this is coming forward. So for instance, she has a construction of strongest postcondition in MSOL for actually not just double pushout rules, but for in this, conditional rules in the setting of GP2. Okay, finished. Yeah, advert finished. Thank you.
Okay, maybe I'm a bit too pessimistic. I'm looking forward to this.
Okay, Fernando, you want to ask a question?
Yeah, a couple of questions. One related to the previous discussion. So the issue, for me, the issue of restricting to monomorphism or not, it's rather a question of your specific needs at one moment or of taste. So it is true that transforming some conditions with monomorphism into non-monomorphic, it means exploding the size of the graph or of the conditions. But it's also the other way around. So it's difficult to say which one is more concise in this sense. I agree with Detlef that if you have more power in transformation than with respect to graph transformation, you would prefer conditions with monos, but not in other cases. In particular, in our case, we started to work with arbitrary conditions because in the work that we have done, extending the conditions, having not full monadic second order, but allowing to reason about paths, and then working with only monomorphism, it was almost impossible. While working with arbitrary morphism, it was simple. That's why we did it. Besides this, the other question is, so there's one paper relatively recent, I think it's 2017, by Filippo Bonchi and Fabio. And I don't know if it has a third author, showing that a confluence, a local confluence, if you have termination, is decidable when you work with interfaces, with graphs with interfaces. I don't know if this translates to the case of reactive systems or not.
Yes, I know. I think it's an ESOP 2017 paper. Yeah.
Maybe,
actually, I mean, the paper contains many other things. So I think it also it's about rewriting for symmetric monadic category framework and so on. I mean, this is not the only result, but actually this result that if you enrich graphs with interfaces and keep track of the interface, and then somehow the confluence check turns into an if and only if. This is exactly what I said. So I talked with Filippo about this. So this result was already in our 2011 FST and TCS paper, and they kind of did it independently. But okay, there's much more things in this other paper. It's very interesting, but this was already known, yes.
Okay.
Okay, very good. So any other questions? Just saying there are interesting papers being posted in the chat as well related to the questions that we just discussed. So Paul-André posted one and Lean posted one. So that's useful. Thank you very much for that. So I mean, we are sort of we used up the time that we had, and if there are no further urgent questions, I would suggest that we finish the scientific part of that. And I think now the idea is that whoever wants to do so just hangs around for a friendly chat. Nick? So we just stay here, or what,
Yes,
what is the plan?
First of all, thanks a lot to Barbara for a really nice talk. I think it's a very, very good way to start this. And just give me 1 second to stop the YouTube stream. Unfortunately for our YouTube viewers, we will now be offline.